Okay, we are now going to go through the fission and fusion POGIL. What I would like you to start with, read through the first 2 pages of the POGIL, look at the models, and then attempt the problems on page 3, 1 through 6 first, and then come back to this video and we'll watch the answers. Okay, hopefully you have completed by now problems 1 through 6. So let's look at them. What is fission? Well, I have to go back up here and scroll and look at the pictures. So I see there were 2 models. There was a fission model and a fusion model. In the fission model, you had this gigantic nucleus and a little tiny neutron coming in. And what happened is it split in 2, and it gave off a lot of other little pieces as well. So a fission process, it comes from the same root word as a fissure, like in the ground. A fissure is a big split in the ground where you can fall in and get hurt and things like that. So a fission here is where this nucleus, this big nucleus, is going to split down the middle here. Maybe not exactly down the middle, as we'll find out. And split into smaller pieces. So fission, the process of fission, is a large nucleus. This only happens in the center of the atom, splitting into smaller pieces. All right, that's how we're going to define nuclear fission. 2 asks, what is fusion? So if I look at the fusion diagram, you have these little pieces coming together like so. They were colored, if you like. Okay, and once they were done, they became one big piece, and this little guy got kicked off, but mostly you had 2 nuclei coming together. Again, the root word is fuse. You're fusing pieces to make larger pieces. So fusion is the opposite. If fission is a large nucleus that splits into smaller pieces, then fusion combines smaller nuclei into larger nuclei. That's it. You could view them as opposite processes. One is breaking into smaller pieces, one is taking smaller pieces and fusing them into larger pieces. Okay, 3. What is the difference between deuterium, and they give a symbol, and tritium? Here's deuterium, and here is tritium. There's a difference, okay? Well, to see the difference, all we have to do is draw them. Here's the deuterium. Deuterium has 1 charge and 2 mass, and we're only talking about nuclear particles here. So inside the nucleus, you only have 2 kinds of particles. Particles that have mass and charge, which are protons. Protons in the nucleus are positive. They have 1 mass and 1 charge. And you have neutrons, who don't have charge. They have 1 mass, but they have 0 charge. So when we look at this number, we have, that's the charge down here. That's the mass. Well, look at the charge. There's 1 charge. Only 1 type of particle in the nucleus has charge, and that's a proton. So a deuterium has 1 proton. The mass is 2. Well, if he has a proton, the proton is worth a mass as well. But in order for him to have a total of 2 mass, he needs to have some other form of mass. But he can't have another proton, otherwise he would have 2 charges, so he must have as well a neutron. So a deuterium atom, if you were to look at its nucleus, you would see a proton, positively charged, and a neutron, neutral. Alright, that's easy. Now, up here with the tritium, 1 charge. He also has a proton. He can only have 1 proton because he only has 1 charge. But he has 3 mass, so he needs 2 more massive particles. Well, the other 2 have to be neutrons. So a tritium is a heavier version of hydrogen. It's got extra mass. So that's the difference graphically. The difference between deuterium and tritium is tritium has an extra neutron, making it heavier. 4. What quantities are conserved in a nuclear transmutation? So let's look at some nuclear transmutations. I'm just going to take one of the fission equations that they gave us. They gave us this one, U-235, 92, plus a neutron, turned into a barium-141, it also gave us a krypton-92, and it gave us 3 neutrons. Alright, there's a nuclear reaction equation. What quantities are conserved is the question. Conserved just means that you get back what you started with. If you started with this amount of something, you end with this amount of something. So let's look at what we start with. We start with 235 mass, and you also have another mass. So you actually start with a total of 236 mass. You start with 92 charge on the uranium, 0 charge on that neutron, so you also start with 92 charge. Then the arrow happens, right? Then we go to the right, and it splits, and it turns into something new. What does it make? Well, it makes 141 mass in the barium, 92 mass in the krypton, and 1 mass on each neutron, but there are 3 of them. What is that? That's 141 plus 92 plus 3, and it looks like that. It's adding up to 236 mass. Let's look at the charge. 56 charge and 36 charge, and the neutrons don't have any charge. So 56 plus 36 should give us 92 charge. So we started with 236 mass, we ended with 236 mass. Started with 92 charge, we ended with 92 charge. So to answer number 4, what quantities are conserved in nuclear transmutation? Both of them are, so mass and charge are both conserved. We get the exact same total mass back as we started with, and we get the exact same total charge back that we started. And I'll bet if you check all the other equations that they list in that model, they all conserve mass and charge. Alright, number 5. The fusion equations show the production of atoms of several different elements, even though each reaction begins with isotopes of hydrogen. Knowing the starting elements, can one predict what element will form as a result of a given reaction? Explain why or why not. A lot to unpack there. So if you go through all of those fusion equations, look at the different types of hydrogen. We had deuterium, so I'm looking at the model number 2. And I'm looking at there are 3 equations written at the bottom of model 2. We have deuterium plus deuterium turning into tritium and a proton. We have a deuterium and a tritium going to a helium plus a neutron, and we have 2 tritiums making a helium and 2 hydrogen atoms. So 3 different reactions. And it says, knowing the starting elements, can one predict what element will form? I'm going to say, according to those 3, it doesn't look like it. We're going to say no, but we need to explain it. And here's the reason. Even though, if you look at the left side of all of those equations, well, excuse me, there was some helium in the last one. But looking at the 2 equations on the left, both of them start with hydrogens on the left. We have hydrogen plus hydrogen on the top and hydrogen plus hydrogen on the bottom, but they don't make the same thing. One of them makes tritium and a proton, one of them makes helium and a neutron. So no, we can't just say that if I add 2 hydrogens together, I know what they're going to turn into, because, here's the because there are different isotopes of hydrogen. Some hydrogens have a neutron, some have 2 neutrons, some don't have any neutrons. So no, because there are multiple isotopes, we'll call them isotopes, Not just of hydrogen, but of every element, so of each element. So just knowing that you started with that element is not enough. If you knew the specific isotopes, you could probably make a better guess. All right. The fission equations show the production of many different elements, even though each reaction begins with uranium-235 and 1 neutron. Look at that. Yep, every single one of them is uranium-235 getting hit with a neutron. How is this possible, given the conservation laws for nuclear reactions? Well, in other words, it's saying uranium splits because it got hit by a neutron, and sometimes it makes, like we saw, the krypton and the barium. But if we look at those reactions, one atom might split into krypton and barium, but another one looks like it splits into tellurium and zirconium, right? Or neodymium and germanium. There's a bunch of different products we can split into. And the main reason that uranium can do this, what makes it available, it's so big. And there are math works multiple different ways. So I'm just going to make a real simple example. Imagine you had 100 neutrons packed together in some big ball, right, of neutrons, and you split. You could split 50-50. That's one way. You could split 49-51. There are many different ways to split that uranium atom in half. Not even in half, it doesn't have to be evenly split. So this uranium atom, when it splits, depending on what it splits into, it can make different products. And it doesn't have to always go to the same way. So that's kind of the answer to this question. There are lots of different ways to split as long as uranium has more than, 2 pieces. If it was like a neutron and a proton, when they split, there's only one way. It can go to a proton and a neutron. But uranium is big. It's got a lot of choices. Okay, so you've now finished 1 through 6. Next section, the next page is 1 through 5, page 4. Go ahead and attempt all 5 questions on page 4, and then come back to this video and check your answers. Okay, you should have finished by now page 4. We're going to check our answers. So number 1, an equation in the model shows the fusion of 2 deuterium nuclei to form a nucleus of tritium. Suggest another product that might form in this reaction. All right, here we are. Deuterium hits another deuterium, turns into... So they're saying a possible way to fuse these together is to make a tritium atom. Now, obviously, you would make a tritium atom plus, you need to conserve everything, we would have a 1-1 left over. So you would also make a regular hydrogen if you underwent this. It says, suggest another product that might form. And we're going to claim that this is the other product that might form. I think that's what this question is asking. I'll actually do both ways that this could be answered. Okay? So if you make tritium, like so, notice that before there were 2 and 2, so after there are 3 and then there has to be 1. You have to add up to 4. We have to conserve mass. Okay? Before, the charge was 1 and 1, so we had 2 charge, so after it has to be 1 and 1. You have to have 2 charge. You have to conserve charge. So this is one possible answer to this question, that we would also get a regular hydrogen atom. The other way to think about this, because they don't specify that you have to make tritium, is if you didn't make tritium, what would you make? Well, you could also just make this. Well, there's 1 charge and 1 charge. You could have a 2 charge, and there's 2 mass and 2 mass. You could have a 4 mass. You could make one single thing that was the product of both of those. And this is your key, 2. 2 charge, okay? We got to find out who has 2 charge. And there's only one person on the periodic table with 2 charge, and that's helium. Look it up. So 2 deuterium atoms could fuse to form helium. That's also possible. So I think either of those answers shows your knowledge of conservation of mass and conservation of charge. So we'll go on to number 2. Describe how to find the identity of the species X in this equation. So let's do the equation. Uranium 92 and 235 plus a neutron is turning into something. Oh, I'm skipping ahead. is turning into neodymium 152. Okay. Plus X and 3 neutrons. Explain how to find the identity of that species. It doesn't say find the identity. I'm going to do it for you anyway. But it says explain how. We can do it using conservation. So we know on the left our charges. We have 92 and 0. So there's 92 charge on the left. There better be 92 charge on the right, or we didn't conserve charge. Well, here's 60. These are 0, so they're not going to add anything. So we have to have something plus 60 to equal 92. In other words, this has to have 32 charge. Now the mass of that dude, let's find the mass. 235 and 1 on the left, so 236 on the left. We have 152 and 3, because there's 3 neutrons. So 155 on the right plus something has to equal 235. I believe that means that has to be 80. Check my math on that one. So now you just have to look up whoever element 32 is. And I don't actually, oh gosh, germanium is element 32. So X would be a germanium atom. Now notice I actually didn't have to do the mass for this in order to know that this was a germanium atom, because the 32 charge tells me who it is. But I do need to, if I want to tell who the specific isotope is, germanium 80, then yes, I do need to know the mass, because germanium 80 and germanium 79, those are different isotopes, and you want to make sure. Okay. So that's number 2. 3. What is missing in the following reaction? Okay, well let's do this again. So uranium, this is 235, 92, and a neutron, always a neutron, is going to turn into something. And we're adding to that something a rubidium 90. And we're adding 2 neutrons. So we got to figure out who that somebody is. Again, 92 charge here, so this side has to add up to 92. So whatever 37 adds to become 92, looks like that has to be a 55 charge. Okay, then on top, 235 and 1 is 236, so 90 and 3, or 2 this time, sorry. So we have a 92 on top. 92 plus something has to equal a 235, which is a 143. Okay, 55 and 143. Let's find out who element 143, or 55 is, because the bottom number is the one that matters. Element 55. Looks like cesium on the periodic table. Has 55 protons. All right, there you go. Not too hard. We're just doing adding and subtracting for fusion. That's all. All right, going on to number 4. Number 4, an atom of uranium-235 absorbs a neutron and produces an atom of antimony-125 and 4 neutrons. Identify the other nuclide formed in this reaction and write an equation. I'm going to do the equation first because that makes this easy. Uranium 235. It doesn't tell me the charge on that uranium, but I can look that up in the periodic table. If you look up U on the periodic table, it's always 92 protons. And it says it absorbs a neutron, so I'm adding a neutron to that uranium atom. And produces, anytime you see produces, that means there's an arrow. We're turning into something new. Produces an atom of antimony 125. Antimony 125 there. And I'm going to have to look that one up. Antimony is 51. Right there. Okay, so antimony 125 is produced, and 4 neutrons, plus 4. Excuse me, I combined two steps there. 4 neutrons. Each neutron is 1, 0. Okay. So we need to know what else is formed, because as it stands, that does not conserve charge or mass. So let's look. Again, 92 on the left for charge, 51 plus 0, so I need 51 plus something to equal 92, which looks like 41. And then on top I have 100, sorry, let's do the left side first. 235 and 1 is 236, so I need to add 125 and 4 neutrons. So 129 plus something has to equal 235. Let's do that. I'll do that on my calculator here. 236 and 129. So I've got to get 107 on top. Come on, stylus. 107. So now I need to know who is element 41. Look that up on my periodic table here. Niobium. Oh gosh, I'm out of room. NB. All right. There's the equation. My answer is niobium 107. You could write this as NB-107 if you like. Just like they wrote U235. And lastly, let's do the last one here, number 5. Identify the following equations as fission or fusion. Okay, the first equation is deuterium plus deuterium going to tritium and a proton. Those are two small nuclei getting together to form a bigger nucleus. Tritium is bigger than either deuterium. And so we will say that is a fusion for the first one. The second one is a uranium with a neutron hitting it, and it splits into barium and krypton. Looks like it's splitting apart. It's fission. The third one is a uranium getting hit with a neutron, splitting into xenon and strontium. So that is also a fission, a split. And the last one are 2 helium atoms, 2 helium-3 isotopes smashing together and forming a helium-4 isotope, which is bigger. So we would say that's a fusion. Okay. All right, you got 3 more to go. 1, 2, 3 on the last page. Go ahead and try those, and then come right back here to check your answers. Okay, hopefully you have finished the packet. Come and let's look at number 1. What is the source of energy in fusion and fission reactions? Explain your answer. So this was research. You would have had to go look this up. This has to do with one atom, and that atom is iron. In fact, I believe it's iron 65. I'm going to look this up. I'm going to do my research really quick. (56) Iron 56. That nucleus is the most stable nucleus possible. And here's what I mean by that. Let's say you had something smaller than iron 56, and I'll take the tritium and the hydrogen nuclei. Definitely smaller, right? They don't have the same mass as iron. Their nuclei are smaller. And they fuse together to form helium. Okay? That process of taking smaller elements than iron and fusing to make a larger element, getting closer to iron 56. Not quite there yet, but it got bigger. So if you're smaller than iron and you make yourself larger by fusing with another nucleus, here's what happens. You start off at a certain energy level. You start off, let's say, here. And then you turn into something new, and by turning into something new, you lower your energy level. And lowering an energy is actually stabilizing. Whenever you're at high energy, you're unstable, you got too much energy, and then you let it go and you become more stable. So anything smaller than iron 56 that fuses and gets bigger does exactly this right here. It lowers its energy and becomes more stable. Okay? Let's look at something else. Let's look at something larger, like uranium, 235, bigger than 56. When he splits, and forms two smaller nuclei, okay, he does this. His energy starts high and goes low also. So this is the takeaway. He becomes more stable by splitting. If, go back up to our iron here, 56 is that magical number. If you are smaller than 56, you become more stable by fusing and trying to get closer to the 56 number. If you are larger than 56, then when you split apart, you become more stable. Now that's not to say you can't go the other way. For instance, let's look at a helium atom. Helium, if helium can, this is completely possible, split and form a hydrogen and a tritium. That process happens. You could do this with a particle accelerator and split apart a helium atom. Totally possible. But when you do that, because you are smaller, helium-4 is smaller than iron-56, if you split when you're smaller, you have to gain energy. Somebody has to give you energy to make you split apart. And so you become less stable, and that's not favorable. In nature, processes that lose energy can happen instantaneously, can happen what we call spontaneously. But processes that absorb energy are harder to do. Somebody has to supply that energy. And the same is true of large things that try to fuse. So uranium, we could take a uranium, we could take a uranium-235, smash it into another uranium-235, these are huge atoms, and fuse them into some humongous atom. It would be gigantic. But that would take energy. That would take a lot of energy. And so it's not making it more stable, it's making it less stable. And so when we look at things like, if you go to a nuclear power plant takes uranium and splits it, because if you split the uranium, you get energy back. It releases energy. It gets rid of some of its energy, and we can take that energy and use it to make electricity and things that we use. Okay? You would never see a power plant like this, because that power plant would lose energy. You would be coming out with less energy than you started. That's no good. It would cost energy, and we don't want that. We want to produce energy. So if you want to give back energy, you have to either be smaller than iron and fuse together, or you have to be bigger than iron and split apart. Long answer. A lot of research. All right. Number 2. Name one problem associated with the use of nuclear energy and briefly explain why it is a problem and identify how that problem might be addressed. Now, when they talk about nuclear energy, they can mean fusion or fission, actually, although currently we only use nuclear fission to make electricity. There's a place in Europe right now that is experimenting and is trying to make a fusion reactor. And while we have created fusion in the laboratory, we have not turned it into a useful product like electricity yet. So let's look at some fission reactions. Currently, if you take uranium and you add a neutron to it and split it apart into smaller pieces with more neutrons, you get energy. But you get these neutrons. And here's the thing. Well, let's take a perfectly healthy atom, like carbon. This is what you're made of. You're made of mostly carbon, like so. If there's neutrons around just flying at you, and they hit your carbon atoms, they can fuse, because carbon is lower than iron. This is an energetically favorable thing. So let's say you get hit by a neutron, and your carbon turns into carbon-13. You have some carbon-13 in your body right now. It's not that bad. And actually, carbon-13 is a stable isotope, so you probably wouldn't notice too much difference. Okay? But if you got bombarded with neutrons for a long period of time, that carbon-13 could also get hit with more neutrons, if there's more of them around, and turn into carbon-14, and now we're getting unstable. Now we're making this carbon too big, and it's going to try and fall apart. Carbon-14 does this. Carbon-14 spontaneously undergoes a decay, kind of like a fission, turning into a nitrogen atom and an electron. So if you sat in a stream of neutrons, all the carbon in your body would eventually turn into nitrogen. And nitrogen works completely different. It makes different molecules in your body, or it's put in different places. And so the structures in your body, the cells would start to warp and change. It might mess up your DNA. There's a lot of things that could go wrong if we changed all of your carbons to nitrogens. Your body would not function the same way. And it doesn't just have to be carbon. Anything, any material that soaks up neutrons long enough will change into some other material and no longer be what it was originally. You will have changed it over time. Dangerous stuff. So as long as you have this giant nuclear power plant and it's got this fuel rod in the center or fuel rods in the center, etc., and they're spitting out neutrons in all directions, the walls will eventually change from what they used to be, and maybe we have to shut the power plant down. If there's people around and the neutrons get out, like eventually this fuel rod is going to not be useful. I mean, fuel rods have a certain time period where they're producing enough energy, and after a while they have fallen apart so much that you have to replace them. Well, what do you do with a spent fuel rod? Because the spent fuel rod is not producing as many neutrons, at least not enough to keep making electricity with, but it's still producing them. I mean, you could go and bury that fuel rod really deep in the ground, but it's still going to emit neutrons all around it, which means the ground around it is going to start to become radioactive. It's going to start to decay into things that are not dirt. The dirt will change into other molecules. You will get different, and that will keep going. So imagine this layer of dirt changes to something radioactive, and then it radiates some stuff, and it keeps going up. Eventually that's going to seep into wherever. It could get into water, it could get into your food, your plants that you're eating. So there's a danger in trying to use nuclear fuel in that anything that produces neutrons produces waste that you have to get rid of somewhere, hoping that those neutrons don't come back to you sometime in the future and poison the stuff that you use for food or for other resources, because neutrons can be destructive. How might this problem be addressed? There's a lot of ways you might have seen. One of the ways that they do it with spent nuclear fuel rods is they put them inside a big concrete container. They fill it with concrete, and they figure that by the time that concrete corrodes enough, that this material will have decayed so much that it's not going to be dangerous. We hope. So that's not a great solution, because essentially what we're saying is this is going to take me 20,000 years to decompose. Well, I'm not going to be alive then, so my grandkids are going to have to deal with that, but not my problem. Not a great solution. One of the solutions people are looking at is a fusion reaction that fuses, oh gosh, I think it's 3 heliums. And it forms, no, that can't be right. Well, let's assume this is correct. Let's say you could fuse 3 heliums into a carbon-12. I'm getting it wrong. But if you could do this, and it gave away energy or something, which it should... Oh, that wouldn't be a carbon-12, would it? No, that would be a carbon... Yeah, it would be a carbon-12. I can do math. Haha. If you did this reaction, notice this... Oh, hey, stop that. Oh, let's just pretend I circled it. That reaction conserves mass and charge, but it does not produce or use neutrons. So you don't need a source of neutrons, and you don't create a source of neutrons. So that fusion reaction would not poison the environment. Now, unfortunately, the current... for that to be viable, it would have to produce a lot of energy, and I don't think this particular reaction produces the kind of energy that we could use to make a significant amount of electricity. But that's what people nuclear physicists are constantly researching, is are there more what we call aneutronic reactions that don't produce neutrons, because if we had that, there would be less nuclear waste. All right, last one on here says, number 3, says, during the 1950s, when many countries performed above-ground tests of nuclear weapons, there was much concern about the radioactive fallout when the byproducts of uranium fission landed on populated areas. One major concern dealt with the fallout of radioactive strontium isotopes and a suspected link to increases in leukemia and bone cancer. What part of the body might absorb strontium? Explain your answer. Well, there could be a lot. I'm going to do some quick research to follow you up here. I'm I'm going to guess it's your intestines. Let's see what they say. Ah. Okay. It looks like strontium is absorbed. So here's strontium. Your body absorbs strontium the exact same way that it absorbs calcium. And that should make a certain amount of sense. If you look at the periodic table, calcium and strontium are in the same family. So your body essentially doesn't tell the difference between this has to do with their electron structure, or it doesn't tell it well enough not to absorb the strontium. So strontium then, where do you find calcium? Well, you find it in your teeth and your bones. Okay, those are places of high calcium concentrations relatively in your body. And so what people were finding is a correlation between absorbing strontium-90, this dangerous strontium isotope, and like bone cancer. Because if you think about it, just like I showed up there, if you have a bone, I'm going to try and draw a bone here. Okay? Your bone is built with a lot of carbon and some calcium. Well, if there's a lot of strontium, if you're like breathing in strontium or something, or ingesting it, because you happen to have someone set off a nuclear bomb that left strontium all over the place and it got into the water supply or the plants or whatever, you get it into your body somehow, and your body says, man, this bone is falling apart, I need to make some more, and so it fills in a gap here with some strontium instead of some calcium, but that's radioactive strontium. Now you have this thing shooting neutrons into your bones, shooting them into all the little cells there. And so you are now absorbing a whole bunch of these neutrons, and if those neutrons change your body atoms into other atoms because of radioactive decay chains, then you have run the risk of altering your DNA, your structures, your proteins, and cancer is something that can come of that. Nasty stuff. Okay. So there you go. Now we are on our way to being experts of fusion and fission.